Everyone, it's Mahesh here. So today I'm going to tell you the velocity distribution of model 2 continuation. So velocity is always vary across channel because of friction along the boundary. The maximum velocity usually found just below the surface of the water or at the bottom. Okay, so this is the figure of velocity in a rectangular triangle, how the velocity will be there. Okay, so see here the distribution of the, so this is the rectangular triangle and the distribution of the water with respect to the velocity. Okay, this is the center line. Okay, and see the arrows, and this is the elliptical shape, and with respect to this is the cross section of this. Okay, then this is the for the trapezoidal canal. Okay, so in this typical velocity and shear stress distribution in a open channel. So figure A, velocity distribution through the cross section. So this is how the cross section the velocity has been distributed. And figure B, shear stress distribution on the wetted perimeter. Shear stress distribution means, so here see wetted perimeter means, so this is the trapezoidal figure or shape, and this level the water is stored. So from this incline and this incline and this horizontal portion, it will be the wetted perimeter. Okay, so this line indicates actual distribution. Okay, then dotted line indicates the uniform distribution. So this is the uniform distribution, bold line, and dotted line indicate the uniform distribution of the stresses. Okay, now coming to the Sajji's formula, that is nothing but V is equal to C into root of mi. Okay, where V equal to root of W upon P, that is nothing but A upon P into sin I. I will call this as equation 1, and M is the hydraulic depth, and R is the radius, and this I will call as 2, and where C is the Sajji's constant. You know that Sajji's formula V is equal to C into root of mi. So this is equation number 2. So substituting the equation 2 in 3 in the equation 1, then V equal to C into root of mi into sin I. For smaller values of I, sin I equal to tan I, that is equal to I. So V is equal to, therefore V equal to C into root of mi. Okay, then Mannings n. Okay, this is the Mannings formula. So such as formula can be also used with the Mannings roughness coefficient. Okay, where C is 1 upon n, that in raised to R is to 1 upon 6, where R is the hydraulic radius and n is the Mannings roughness coefficient. Then it can be related to the Banz's formula. So such as formula can also be used with a Banz's formula, that is equal to C is equal to 157.6 divided by 1.81 plus of rho plus of k divided by root of m, where k is the Banz's constant and m is the hydraulic radius. Okay, next, this is such as formula V equal to C into root of mi, where value of n in the Mannings and Quotas formula can be used depending on the surface of the channel and N. Quotas or Mannings constant. So smooth cement, plaster or a planed wood 0.010. So next one is very smooth, that is 0.011. Smooth concrete 0.012. Glazed brickwork 0.013. Then vitrified clay 0.014. Brick surface lined with a cement mortar 0.015. Earth channels in the best condition 0.017. Straight unlined earth channels in good condition 0.020. Rivers and earth channels in the fair condition 0.025. Canal and river roughness surface with the weeds means small surface will be there, that is 0.030. So this the value of a C n can be assumed for this Mannings and Quotas formula. From this table, depending on the roughness of the channel, we can assume the n values. Okay. Then most economical sections or most economical channels. Okay. So condition first one, the condition for the most economical sections is that for a given area the perimeter should be minimum. Considering rectangular section, okay, then trapezoidal and circular section, these are the three most economical sections. So if the sections must be economical means the cost of the construction should be minimum and discharge should be minimum. Okay. Then types of channels based on shape, that is rectangular, trapezoidal and circular. For most economical sections, discharge Q is equal to A into V, that is nothing but A into C into root of Mi, that is Q equal to K into root of A into I into P, where K is equal to root of AC. If P is minimum, Q will be maximum. So this is the rectangular channel. So the, up to where water is stored from this height, and this is the bed width, and this from this side it is a wetted perimeter, and this is the height of the channel. Okay, so rectangle channel for most economical sections, P should be minimum, that is dP upon dd equal to 0 for rectangular channels. Therefore, area equal to breadth into depth. Therefore, B equal to A divided by D. Therefore, perimeter P is equal to B into 2 times of the depth. So, A upon D plus 2D, that is equal to equation 2. For most economical section, P should be minimum. That is what P is weighted perimeter should be minimum. So, dou P upon dou D is equal to 0. So, therefore, B equal to twice of depth, or D equal to P by 2. So, for the most economical channel, here the that is M is equal to D by 2 and A equal to breadth into depth. Okay, so this is the trapezoidal channel. Normally we'll be saying here for the irrigation purposes. Okay, trapezoidal channel for most sections of the trapezoidal channel, P should be minimum. Therefore, dou P upon dou D equal to 0. So this is the trapezoidal. So A equal to B into N into D, that is equal to B equal to A upon D into N into D. 1, equation number 1. Therefore, P perimeter P equal to B into twice of D into root of N square plus of N. Root means this inclined portion n square plus fn, that is called a upon d into n into d plus 2d into root of n square plus 1. I will call this equation 2. For most economical section, p should be minimum. So therefore, do p upon do d equal to 0. So therefore, m is equal to d by 2 and theta is equal to 60 degree. Okay. So this is for the circular sections. So here this is circular section. This is the point centro, and this is the chord, and this is the radius. Okay, this is the radius r. So for maximum velocity, d equal to a upon p. So therefore, a equal to r square and 2 theta and sin 2 theta upon 2. One equation 1, p equal to 2 times of r into theta 2, m is equal to a upon p, that is equal to r upon 2 t theta minus sin 2 t upon 2 that. Okay. Equation number 3, for maximum velocity, dou m upon dou t equal to 0, therefore theta is equal to 128 degree, the 45 degree. So 0.18 d, m equal to 0.3 times of d. We know that q is equal to a into c into root of mi. Therefore, a into c into q root of I, that is q into a, q root of a q upon p I into c, and I, c and I are the constant. Okay. So for maximum discharge, that equal to 0, that is equal to 154 degree, and d equal to 0.95 times of d. Okay. So simple problem. A trapezoidal channel has a side slope of 1 horizontal to 2 vertical, and the slope of bed is 1 in 500, 1 in 1500. The area of the section is 14 square meters. Find the dimension of the section if it is most economical. Determine the discharge of the most economical section if c is equal to 50. Okay. Slope n is equal to horizontal divided by vertical, that is equal to 1 upon 2. Bed slope they are given is I equal to, that is 1 in 1500, 1 divided by 1500. And from this figure, this is the depth and this is the breadth, and this inclined portion, this is width is half of d. So area of section is a equal to the given 40 square meters. Then here it is 40 square meters. So this competency is equal to 50, they are given. So for most economic section, using equations 16.1 from the previous, b plus 2 n upon d, n upon 2 n d upon 2 is equal to d into root of n square plus 1, or b plus 2 into half of d divided by 2, that is equal to d into root of half square plus 1, or b plus d by 2 equal to d into root of 1 upon plus 1, that is equal to 1.18 times of d. Therefore, b equal to 2 times of 1.118 into d minus d, that is equal to 1.236 times of d. Equation 1. But area of trapezoidal section A is equal to b plus 2 into n into d divided by 2 into d. So that is a b plus n into d into d, that is equal to b equal to 1.236 d and n equal to 1 by 2. So putting these values, we will get 1.736 d square. But we know that area equal to 40 square meters given. Therefore 40 equal to 1.736 d square, and therefore d equal to root of 40 divided by 1.736, that equal to 4.80 meters. Substituting the value of d in the equation 1, we get b equal to 1.236 into 4.80, 5.983 meters. Okay. Therefore, discharge for the most economical sections, headed mean depth for the most economical section is m is equal to d by 2, that is equal to 4.80 divided by 2, that is 2.40 meters. Therefore, discharge q equal to A into C into root of mi. A is 40, C is constant 50, root of 2.40 into 1 divided by 1500, that is equal to 80 cubic meter per second. Okay, thank you. In next session, I will be telling you the next part of the